Our next speaker is Professor Volodymyr Kuleshov from Cornell, and who will tell us about modern diffusion language models.
Thank you for having me. So I'm going to be presenting some work together with my research group at Cornell, and I'll be covering some recent work in the application of diffusion for language. So we're going to see some basic techniques for building diffusion language models, and then some more advanced techniques that are needed to deploy them in a diffusion language model, and a large-scale diffusion language model, using recent open source models as examples. So I would like to start the talk with this slide that shows three types of scaling laws that have been contributing to the improvement of language models in the last several years. Between 2020 and 2024, a lot of the gains in language modeling performance have come from scaling pre-training. And that was possible using three key ingredients: a lot of data, a lot of compute, and a training procedure, a training algorithm that could use this data and the compute, because it was designed from the ground up to be very parallelizable across GPUs that are available today. And by that, I mean the transformer architecture. But if you look at the progress in language models in the last 2 years or so, most of the gains have come from scaling post-training, especially using techniques based on reinforcement learning, as well as inference-time scaling. And both of these techniques are heavily bottlenecked by our ability to generate from the model quickly, both in reinforcement learning and in inference-time scaling. However, the current algorithm that is used for generation is inherently sequential and not parallelizable. In fact, I would draw an analogy to recurrent neural networks, which was the dominant architecture before transformers. And RNNs did not scale for pre-training because they were inherently sequential and hard to parallelize on GPUs. So the high-level idea I want to convey in this talk is that in order to continue the gains that we've had in pre-training and carry those over to post-training and inference-time scaling, we need to develop methods that we need to develop language models that are fully parallel both in training and inference. This is the kind of models that I would like to talk to you about in this presentation. So specifically, I would like to present a series of models that is based on diffusion, so that achieves this goal of parallelism by adopting techniques from diffusion. What that means is that instead of generating tokens sequentially one at a time, a diffusion method, a diffusion LLM, would generate tokens all at once. It would generate sequences of tokens by starting with some initial guess of what the sequence is and refining it in parallel over time. So this approach has a lot of advantages over autoregressive modeling. The first one is speed. Because we can produce multiple tokens per step, we can produce tokens more quickly, we can produce more tokens per second, and this is in line with the goals that I had in the previous slide. Also, because we generate by refining over time an initial guess, the process almost by definition has a form of built-in error correction, which can improve quality. And in addition, I guess in contrast to autoregressive models, instead of making incremental changes to the sequence as we generate, we're able to make global changes, so we can potentially change multiple tokens. We could refine multiple tokens that are far away apart in the sequence. And both of these features, both error correction and global changes, that is helpful in all kinds of downstream applications. For example, in controllable generation, if we would like to generate, say, a molecule having certain properties, being able to do iterative refinement and global edits, that is really helpful. And also, these features open up new axes for scaling compute at inference time. So for example, we can spend more or less time denoising. I guess what I want to say is there are a lot of really appealing advantages of using these models for generating language. Now, for many years, building performant diffusion models was an open problem. And for the long time, there was a big gap in performance between autoregressive and diffusion modeling. In recent years, and since about 2024, this gap has started to narrow. And there are now real-world language models that you can access, both commercial-scale language models, like, for example, this model that in whose development I was very closely involved, called Mercury. This is a commercial-scale closed-source model. And similarly, there's also models coming out from Frontier Labs so this is, for example, Gemma Diffusion, which also came out in, so I guess the first model was February 2024. This model is May 2024. So again, this is just an example of the kinds of how this model would respond to a certain prompt. And since then, especially this year, there have been even more releases. There's now open source models from Google, one called Gemma Diffusion. There's a model called Nemotron Diffusion. So these models are becoming increasingly performant. They have all kinds of advantages. So this animation just highlighted speed. And what I would like to do in this talk is to give you an overview of the kinds of algorithms that have enabled increases in performance in diffusion language models in the last 2 years, and then also the kinds of additional algorithms that are needed to construct these kinds of open source diffusion models. These will give you kind of the key ingredients and some high-level overview of the research advances that are needed to build these kinds of interesting models that you might find today. Okay. Let's see. So first, I would like to spend just 2 minutes giving a kind of a quick, very high-level refresher on the structure of a Gaussian diffusion model, which is the normal kind of diffusion model that we would use. Then we will talk about a very simple example of discrete diffusion, and then we'll spend the rest of the talk on more advanced versions of or extensions of simple discrete diffusion and how they are used in these open source language models that I just mentioned. So so this form of Gaussian diffusion is currently the mainstream algorithm for generating images, videos, and any kind of data that is inherently continuous. The key idea behind all of these models is that generating an output over multiple steps is going to be more efficient than generating it all at once. And concretely, the way that these models generate over multiple steps is by starting from some initial guess, which is noise. In the context of images and continuous data, a natural choice of noise is just complete white Gaussian noise. And then these models produce outputs by gradually refining this noise and making it look more and more like an image. Now, behind the scenes, the way these models are trained to perform this kind of generation is to follow a very kind of consistent blueprint across many different types of diffusion models. And this blueprint typically involves 2 complementary processes. There is a forward process, which can be seen as a form of data generation, which produces trajectories of images being transformed to noise. And then there is a reverse process, which is trained on these trajectories going from image to noise, and it is trained to produce them, but in the opposite direction. So concretely, starting from any clean image, a forward process will just define a sequence of steps by which this image transitions between noise and clean data. And then a reverse process will be a machine learning model that will be trained on these trajectories to run this process from pure noise to get the clean data. And if we have trained the reverse process on a sufficiently large number of trajectories going from image to noise, then it will learn to generalize. And if you give it a new type of Gaussian noise, it will learn to replay it in the opposite direction. So this is a structure that is standard for all kinds of continuous models. And we can use the same structure to define discrete models as well. So in order to define a discrete diffusion model, I'm going to introduce a little bit of kind of symbols and notation here. So let's say that we're now interested in generating discrete data, such as this piece of text. I'm going to represent discrete data as these little blocks here. And this is general. It could also refer to DNA sequences. I guess we're going to have an example with DNA sequences, protein sequences, any kind of discrete data. Let's say we will abstractly represent it as these little squares. Now, the main challenge in extending extending image diffusion to continuous data is defining what noise means, right? We said that a diffusion is effectively doing generation by denoising, so that requires us to define what is noise. And I guess there's two high-level approaches here. One approach is to take the discrete data, map it into a continuous space, and then perform continuous diffusion in that continuous space. The other approach, which today is the basis of a lot of these open source models, and that's why I'm going to focus on it more, is to take the discrete data and define a noising process purely in that discrete data. And the most common process used today, and one that we popularized using work in our research group, is the process of masking. So introducing noise corresponds to masking out elements of this input. And we're going to represent this as follows. So I guess a mask simply means taking an actual token and replacing it to a virtual mask token. Here at the bottom, I will use these white squares as my notation for performing masking. So if I were to summarize mask diffusion in a nutshell, you can think of it now as an unmasking transformer. So we train these models on data, on clean, fully unmasked sequences, which I denote by X. And we define essentially a forward masking process that produces partially masked data, produces noise data by taking sampling a random noise rate between 0 and 1. That is what I'm referring to as T. And then it randomly masks a fraction T, or I guess it randomly masks each token with a probability T. So expectation is percentage T of tokens are masked. And those are represented by white spaces. And I refer to that partially masked data point as Z sub T. So this is how we create those partially noised sequences or partially noised data points. And then we use those as training data for a machine learning model that is typically a transformer, which I'm going to denote by X of theta. And this is going to be a denoising model that will take a partially masked sequence and try to infill the blanks. It will try to produce the clean sequence from the partially masked data point. And I'm sure that many of you see that this is very, very similar to BERT. And the main difference with BERT is that this masking rate, instead of being fixed to a certain value that is a hyperparameter, it is instead sampled randomly between 0 and 1. So essentially, you can think of these mask diffusion models as a form of generative BERT. And the fact that we're training them with different masking rates allows them now to denoise outputs with different masking levels. And that also enables us to use these models for generation. So concretely, at generation time, we start with some intermediate partially masked input, which could be potentially a fully masked input. And then we ask the model to fill in the blanks. And then we keep a small portion of these blanks. And over time, as we fill in more and more of these positions, we get a fully unmasked output sequence that looks like a data point from our distribution if we have trained everything correctly. Yes?
So this is like a erasure, right? So you're basically masking, which is like blocking against erasure as a noise. If you also flip some discrete word into another vocabulary,
yeah.
That's do you consider those as noise as well? Or that's not
yes,
useful?
we can, and I will get back to that in a few slides. But that's a really good question. So the question is, can we flip words? I'll get back to that in a moment. Okay, now this approach is really simple to explain, and we can also map it to this forward-reverse process blueprint that I mentioned earlier in my slide on Gaussian diffusion. We can also define this a mask diffusion model as being made of these two complementary processes. The forward masking process can be thought of as a Markov chain that starts with a clean data point, and at each time step, it masks one of the unmasked tokens in the sequence with a certain probability that's given by a formula, where alpha here is a noising schedule. So you can think of alpha as being a user-defined signal-to-noise ratio that starts at 1 initially, so 1 being no noise, only signal, and at the end it has to go to 0, where everything is just noise, everything is masked, and only signal and only noise is left. So this is a noise schedule that is set by the user, and given this noising schedule, we can define a Markov process, a Markov chain which masks these data points with a certain probability, and by running this Markov process from the clean data point, we'll produce a full trajectory from clean data to noising data, much like we had a trajectory from clean data to Gaussian noise in the Gaussian example. And this will also have the property that in expectation, the amount of blanks in a sequence at time step t is going to be in expectation alpha t. This has this nice property. And now that we have a forward process, we can then consider defining a reverse process that is going to be a learned model, a machine learning model that will be trained to perform this generation process in reverse. Much like in Gaussian diffusion, we started from Gaussian noise and we produce images. Here we're going one step at a time. Here we're going to train a machine learning model to start with masks and run this process in reverse. And I'm going to denote this. So I'm denoting the mask process by Q. The mask process is the unmasking process, the reverse process, is going to be denoted by P. So we might ask the question, how do we construct this reverse process? And here there is a nice trick. The way that we can approach this problem is to consider what would have been the ideal reverse process. And let's just say I want to know what is the ideal reverse process to go from a partially masked sequence ZT to a slightly less masked sequence ZS if I knew X. Okay, in practice I will not know X, but just bear with me for a second. Let's say I knew what the final destination is. So using Bayes' rule, I can compute a formula for this unmasking posterior, and I can essentially derive that it has a simple form, which is that if a data point has been masked, then I will unmask it to its true value X with a probability that has this formula that's a function of my schedule. Okay, so if I knew where I'm going, if I knew X, then there is an optimal form. There's an optimal process for going from one ZS to the next ZT, which is look at the actual data and fill in each position with a certain probability, and then with 1 minus that probability, you still leave it as a mask. So that's the optimal process. Now, of course, and you can derive this using Bayes' rule. Now, the main problem is that I don't know what X is. I don't know where I'm going. But then what I can do is I can train a machine learning model X theta to predict what the final destination should be. And then I perform the same procedure, but instead of using the true data, which I don't know in practice, I choose a prediction for what X is. I choose X theta, and I perform the same procedure with X theta, which means that I take each currently unmasked position, I look at its prediction from the model, and I keep it with a certain probability. I keep the prediction with a certain probability that's given by this formula. Otherwise, I keep it still as a mask, and I revisit this at the next step. So this is a formula for a generative process that if I have a trained model X theta of my predictions, which is what I would get from that transformer that I mentioned earlier, if I were to run this in the opposite direction with this approach, then I would be guaranteed to generate data from my from distribution in which I train my denoising model. And moreover, this generation procedure also happens to define a probabilistic model of the data. It's going to be a latent variable probabilistic model in which the z's are going to be the latent variables. X is the final clean data, and it defines a distribution P of X where the z's are marginal, and so P of X is going to be the average over, or the marginal over all the possible trajectories, over all the possible sequences of z's that could have generated my data X. And sampling from this model corresponds to doing ancestral sampling in the or I guess, generation using my reverse process corresponds to ancestral sampling in the model using this learned denoising model. Okay, now that I have a model, I can ask a natural question, which is, well, how does it perform? And in particular, I can look at its log likelihood as a measure of its quality. And this is something that you couldn't necessarily do for BERT. BERT is just, it's a feature learning algorithm. But if we look at this, at mass diffusion as a way of, as a probabilistic model, I can ask the question of what is its likelihood. Because it's a latent variable model, its likelihood is intractable. So we have to look at its evidence lower bound. And it happens that the evidence lower bound in these models has a very simple form, which is simply an average of BERT losses. So X here is my clean data. Z sub t is a partially noised data point that's sampled from the model. And I am averaging these losses. So here X given log probability of theta of X given ZT is just the cross entropy between the predictions of my model and the predictions of the denoising model when run on a partially masked data point ZT. Cross entropy to the actual clean data. And this noise level T is going to be randomized. So at each point, I will be sampling a different noise rate. I will mask that percentage, and I will look at its cross entropy, and I will normalize each cross entropy term by 1/t. This is the exact same BERT loss that we started with, except that I have a simple formula for averaging BERT losses for every noise level. And this loss corresponds to a principled evidence lower bound on the likelihood of the mass diffusion model. So it's not just a trick for training a mass diffusion model. It is, we're doing principal optimization of the log likelihood. And now this is interesting because log likelihood, or perplexity, which is a kind of rescaling of log likelihood, that is the principled way for evaluating language models, especially autoregressive language models. And now that we have this formula, we can ask the question, how does this perform relative to autoregressive language models? And what we found is that, I guess in a line of work across different groups, including ours in 2024, we were able to measure this perplexity across different data sets. And what we found is, for the first time, at least up to GPT-2 scale, the perplexity of diffusion models, especially mass diffusion models, has been starting to approach the perplexity of autoregressive models. Now, the gap here is different across different data sets, but this is the first signal that it is possible to train these models with a perplexity or with the standard quality metric that is used for autoregressive models, train it such that the quality, according to the standard metric, is comparable to autoregressive models across many domains. Yes?
So the ELBO bound, is that what you're optimizing? But that's still if you maximize that, it's still a lower bound to the true perplex.
Yeah, so that's a good point. For a mass diffusion model, this formula, and this is also, so this formula, and it's also the formula that we're using to compute these perplexity numbers, that is still a bound on the likelihood. In theory, the likelihood could be better. And in fact, there are techniques for computing the exact log likelihood in these models. So there's there's two papers. There's one from our group and one from, I think, a university in Singapore or Japan, and so there's techniques for computing the actual log likelihood, and it is better. So it's actually about 30% better in our measurements if we were to compute the exact likelihood of these models. Yeah, so there's a paper called Dual by one of the students in my group, Gilad. So that one gives like a very thorough analysis and even has scaling laws and shows how these scaling laws improve if you actually look at the likelihood itself as opposed to the ELBO. But that's a good question. Yes?
So a quick question. So here for autoregressive model and your MDLM, is it the same number of parameters, so like compare?
Yes, the number of parameters is kept constant. Across AR and MDLM and SED, and I don't know if I think D3PM as well, and then I'm not sure about diffusion LM, and I think diffusion BERT as well. But yes, that's a good question. But yes, AR and MDLM, yes, and SED too. Okay, so this is, oh, sorry, did you have a question?
Yeah, you had mentioned at the beginning that like a benefit of using diffusion models on sequences is you can kind of like globally iterate on the sequence. but it looked like in the generator process you were describing, once you like generated a token, it remained fixed throughout the like demasking trajectory.
Okay, that's a great question. This is exactly where I'm going next.
Excellent.
Okay, so here I just wanted to give you a high-level overview of a very simple kind of discrete diffusion, although one that is currently the mainstream way of doing discrete diffusion across all kinds of like large-scale open source models. But to your point, this is a good intuitive example, but it's not good enough for building a real diffusion language model. And so what I want to talk about are some of the, is your question, and a few other ingredients that are missing to actually build useful models. Before I answer your question, I also want to point out that there's one very obvious, very clear limitation of these models is that they have been defined to only generate fixed length sequences. Whereas with an autoregressive model, we can just keep adding tokens and generate sequences of variable length. Perhaps the most mainstream approach for addressing this limitation is something called block diffusion, which is the idea that you would run diffusion over blocks or windows of tokens in parallel, and then you would generate the following block of token, again using a fixed length diffusion block conditioned on the previous tokens that you have generated. So this, in a way, allows you to interpolate between autoregression and diffusion. The block size can be of any length. If you care about certain applications, like for example, if you care about biological applications, you might have prior knowledge on the kind of range of the interactions that you would like to capture. If you care about purely speed or efficiency, then you would want to choose the block such that the arithmetic intensity of your algorithm matches the arithmetic intensity of the hardware that you're running this algorithm on, at least in theory. And this approach is used across many models, including Gemma Diffusion, from which I took this figure, but also other methods like LADA, Nemotron. So here, this is an illustration from the Gemma Diffusion blog, where they use blocks of 256 tokens, and then they generate that block. Now conditioned on the previous block, they generate the next block, and so on and so forth. This also provides one important feature that autoregressive models have, which is KV caching. What I mean by this is that once you have generated the block, because everything here still uses a transformer architecture, you can cache the KVs that were used to generate one block, and you can reuse them for future blocks. So this also unlocks KV caching in diffusion-based models. And once you also do block diffusion, then there is a natural question on, in terms of what architecture should you be using for this approach. And there's an interesting insight that if you perform blockwise generation, then there's typically two kinds of tasks that you perform. There is the task of taking a block, a partially masked block, and denoising it. There's a denoising task. And then there's also the task of looking at everything that has been generated before and computing KVs, or I guess activations, or in a general sense, encoding the prompt and everything that has been generated so far. And in theory, those are two different tasks, and they don't necessarily require you to use the same model, which is why a lot of recent models have been moving to an architecture that I would call encoder-decoder, or you could also call it encoder-denoiser, in which the input query and everything that has been generated so far can go into a large, into one large transformer, which will produce some kind of representations, which can be the KVs, which often are the KVs. And then any given block that is being generated can be processed by another transformer, which might share weights with the encoder. This I will call the denoiser or the decoder. And the decoder can be much smaller than the encoder, and it can quickly process and unmask the block until at the end it gets encoded by the encoder for the next step. So this is also an approach that is used in Gemma Diffusion, in Nemotron, and it is a way of improving it's a way of improving inference time efficiency if you can use a smaller denoiser model, and it's also a way of improving training because you might be able to, well, in some papers, like in Gemma Diffusion, they have reused weights for the encoder from an existing model, and for the denoiser, if you make that smaller, then that reduces the number of training flops relative to if you had two models of the same size. I think there's two questions.
So there's also almost like something kind of counterintuitive. Like if you think about writing like long form text, you almost think what is non-autoregressive is basically like the blocks themselves, and within a block you almost think things are kind of autoregressive, like almost like when you write a paper. Like I can write a paragraph autoregressively. I probably can't write like sections autoregressively. So it almost feels like the thing that shouldn't be autoregressive is like the blocks themselves, rather than like the content within block.
I think that's an interesting question. I don't know. I think it depends a little bit on what kind of result you're looking for. I think from a purely practical result, if you're looking to maximize the efficiency of your hardware, this approach is very valid. I think if you care about capturing long-range interactions, I think there's some, you could imagine also injecting this and injecting into this approach and augmenting it with other features, like for example, some kind of latent states, which might describe what you're doing. And there's a lot of ongoing work on, I guess, modeling things in a latent space, or at least kind of encoding your, the previously, the prompt or any sort of context, and then generating condition on that, which might do a little bit more like what you're saying. So this is perhaps not, the final architecture, but I think it goes in a good step for optimizing efficiency. Yes.
Yeah, I was curious how this ends up comparing to the sort of like multi-token prediction optimizations that people put on just the autoregressive thing. I guess it is sort of in the same direction, but it's sort of a different scale. How does those...
Yeah, so this is also a great question. If you are familiar with speculative decoding, speculative decoding has evolved over the last 2 years to actually use something that's very similar to this architecture as well. So there are oftentimes some of the state-of-the-art methods like dspark and dflash, they use pretty much the same encoder-decoder architecture, except that the output here is generated and then it gets verified as a speculative draft by the encoder. This approach also works well. This was a bit of a, this was a big improvement over, say, the Eagle kind of models that were that also had this architecture but were not diffusion-based, which was maybe the state of the art last year. I think it's a really promising approach. I would say the best study of the trade-offs here is in the Nemotron Diffusion paper, which I'll mention a little bit later. So what they did is they trained a single model to perform both block diffusion as well as autoregressive inference. And once they do block diffusion, they can use it as a pure block diffusion model, and they can also use it as, they can use their block diffusion as a speculator. So they have these three approaches that they compare. And their paper is really great. I think if you want all the details, it's really great. But the high-level takeaways are that if you use block diffusion and in the speculative approach, it works about the same in terms of quality. They find the speculative approach being a little bit faster than the sampler that they use for block diffusion. But then they have this kind of upper bound on the performance of diffusion models if you had some oracle information about the optimal ordering in which you would want to denoise the tokens. And that, they call this their speed of light analysis. That is significantly faster than autoregression. And so what the conclusion, than the speculative decoding approach. And so what that means is that there's still a big gap in the design of samplers that you could be using for diffusion models that have the potential to essentially there's in the kind of academic, or at least the best kind of open source academic work with this particular, in the mass diffusion world, because I guess there's also some other types of noise that I'll mention in a moment, there's a gap in the kinds of samplers that you can use today. I think that's the takeaway. Okay, great questions. Yes?
How does like this work? So you change like the training? Like, does it affect how you train?
Yes. So that's a good question. How does this affect the training? In theory, you can use an existing model and you can run inference using, well, okay, so this slide is an architectural change, but this slide might not require you to do any architectural changes. You can oftentimes take an existing model and run it in this mode without any training modifications, but to get the best results, you can also train it. So there's a particular training objective which involves essentially doubling the effective sequence length that you're using. So you essentially run kind of one forward pass on the data where everything is unmasked, and then you have a second forward pass in which you use a certain type of block mask, and then the tokens cross-attend to each other in a clever way, and that would train exactly for the kind of inference that you would be using with a block diffusion model. But it also works reasonably well. If you don't do it, that's something that helps to squeeze out some additional performance. Okay, I just want to, okay, I think I'm going to have to go fast. So thank you for the questions, but let me just try to kind of address the question that we had here, which is the question of iterative refinement. So yes, the point that was made is exactly correct. In the simple mass diffusion example that I gave, you can never go back and fix any mistakes that you introduced. Because of the way that we define the forward process, perhaps if you remember this figure here, we have so the trajectory generated by the forward process, it masks a token, and the token never gets remasked again, or it never gets, it gets masked and it never gets unmasked. So when you train the reverse process, it never sees examples of error correction, and so this process does not support iterative refinement. However, there are many ways of addressing this, and in a lot of existing, in all of these open source models, there are ways of doing iterative refinement. The simplest way is something called remasking, which is a generation time. If you have an error here, so should be she sells, you can either randomly or using a heuristic move tokens back from their clean state to the mask state. So there's various heuristics that you could use for this, and that means that in future cases, in future steps, you can produce the correct token. And there is actually a principled approach for how to do this. There is a different forward and reverse process that you can design that will have this property. But that said, you can also use this approach as a sampler over an existing mass diffusion model, and it also works really well. Yes?
So my question is that if we really were able to estimate the joint probability of these two mask token given seashells, then is it possible to have this mistake of shear cell?
Yeah, so that's a really good question. The reason why there is this mistake is because typically the transformer that is used to denoise is fully factored across every position, and so here these two tokens are correlated, and a fully factored distribution would not be able to kind of put mass only on the two sequences that are valid. This is definitely a limitation of regular mass diffusion. There's all kinds of work on correcting it, from changing the architecture of that transformer. So there's kind of work on copulas, for example, or just the transformer could output not a fully factored distribution, but one that has correlations. There's one line of work. And of course, there's all kinds of interesting work on continuous diffusion these days, which does not require you to perform a discrete sample at every step. So you keep things in an intermediate state during generation, and that has also the promise of fixing this. So yes, if you can address this problem, then you can potentially sample faster, or you can have fewer error correction steps.
Just as the postponed question, so that speaker can finish.
Yeah, so how much time do I have? Sorry, this is
5 more minutes.
5 more minutes. Okay, all right, let me go really quickly. One nice feature of remasking is that you can now do more or less of it, which enables you to scale computation, and you can get higher quality by spending more time denoising. This is interesting because it forms a new axis for inference time scaling that regular autoregressive language models don't have. So you scale inference time compute by thinking more you spend compute along the length dimension. Here you could spend effort along the time dimension to denoise more and to improve quality. Now, of course, the other approach that you could use is just to switch from a mask noising process to one that that has built-in error correction. The popular one is called uniform state noise. It's called uniform noise, where you basically flip tokens at random. There's also all kinds of nice simplified and optimized loss functions for this particular domain that you can use. And this is also the noise process that's used in, for example, the Gemma series of models, which you have here. So this is, I'll just mention that briefly. And I will also add that iterative refinement, once you can do this, unlocks another nice feature of diffusion models, which is controllability, which means that you can also use these models to effectively produce outputs that have certain properties. So for example, let's say you want to generate an X, which could be a biological sequence, that has some property Y, which could be whether it binds to some target site. In conditional generation, you would like to sample from X that have a high property where Y is maintained, or Y, if it's a continuous variable, then it's really high. And in practice, when you try to do this, most algorithms have a trade-off where you could either spend you could either have weak guidance, and then you have a model that doesn't really produce this property, or you could enforce it more strongly, but then you could have degenerate outputs. You could have degenerate molecules, but they're predicted to have a very high property Y. So in practice, there's a Pareto frontier, and discrete diffusion, because it can do this iterative refinement, it can achieve a better Pareto frontier than autoregressive models. There's techniques that are based on classifier-based guidance and classifier-free guidance that are mainstream for continuous diffusion. There are extensions of these to discrete diffusion, and they work great. I'll just go straight into kind of a few examples. I'll conclude in the next 3-ish minutes with just a few examples of how all of these techniques are used. And if you look at diffusion models out there in the wild, there's the first area where these models have found a lot of interesting applications, in part because of their controllable generation capabilities, has been in AI for science. One interesting example is the ESM3 family of models, which was published in 2025 here. That model is essentially MDLM. It uses pretty much the same sampling algorithm as I have shown you at the beginning of the talk. It is scaled up to 100 billion parameters, and it's trained on amino acid sequences. So this is used for both representation learning, and also in this paper they explore how it can be used for generation. So this is one area of application. You can also extend the same thing to DNA models, where so this is a work in collaboration between my group and BioNTech so BioNTech, the pharma company, where essentially the same approach as in ESM3 was applied to DNA sequences with this additional conditioning information. So if you would like to generate a sequence, I guess you train these models on DNA sequences and other information, for example, labels of whether this is a regulatory region or not. And then once you have trained this model, you can use it for conditional generation using these classifier-free guidance techniques, classifier-based, in this case, classifier-free guidance techniques to increase the strength of conditioning. And if you ask the model to generate sequences that are very strongly believed to be regulatory sequences, then we'll produce we tested its ability to do this using a wet lab experiment where we synthesized those regulatory sequences. There's a wet lab that did the kind of real-world experiments, and as you kind of crank up your guidance and controllability term, you can get sequences which are more likely to increase the expression of the target gene. So these are two highlights from biology, but I do want to mention that there is, of course, a lot of exciting work right now on diffusion for language, and this has really taken off since about 2024. I'll just highlight a few brief examples. Maybe the first open-weight diffusion LLM is this model called LADA. What LADA has reported in their paper is increase in benchmark performance that tracks and sometimes even performs better on certain benchmarks than autoregression as you train the model in more flops, as you train it on more data. There is an improvement in benchmarks that is comparable to that which you would see in the same autoregressive model that's been designed to match the same flop budget. And this is a model, of course, that's available that you can use. It's a mask diffusion model that here, on all of these benchmarks, it runs with block diffusion, and it supports all kinds of techniques for post-training and inference-time remasking and things like that. There's a lot of interesting work from Nemotron, so I'll go over quickly, but this is what I mentioned with regards to your question. This is also a block mask diffusion model, but it has these 3 interesting modes, which you can use to compare speculation and diffusion and autoregression. It's also very fast. And also there is commercial efforts. So here Mercury 2 is a commercial scale model that you can access, which runs at over 1,000 tokens per second and it has performance that is comparable to models like Claude Haiku here or GPT-5 Mini. So it's comparable in quality to a lot of speed-optimized models, but it can run much, much faster. And interestingly, it can even match the performance of specialized inference chips like Grok or Cerebrus while also maintaining the same quality. So this is a smaller model. This is Mercury Mini, an older model. It's compared to Llama 8B that was run on these chips like Sembanova and Grok, and the speed is comparable, but and the speed is comparable and the quality is also comparable or even a little bit better than that model. So yeah, it's an interesting direction. I think the inference time efficiency of these chips is a really exciting direction that has the potential to ultimately kind of go back and improve those scaling laws that I started the presentation with. And I think that's one of the exciting promises of diffusion models. So I will end here. Thank you for, I know I'm a little bit over time, and yeah, kind of this, I'll just summarize that we have, diffusion for language is something that has accelerated really quickly over the last couple of years. There's real-world open source models. There's all kinds of interesting research being done in this area. I encourage you all to take a look. I think it's a very exciting field.
Let's take one or two questions.
Yes?
So I'm trying to map this to diffusion for images.
Mm-hmm.
What is the relationship for images, the relationship between noise, when you do reverse diffusion, in the beginning of the process, you first choose the identity of the object, and then gradually add the details.
Mm-hmm.
The model does that. And that comes from the relationship between the structure of noise versus signal. What is the relationship between the structure in the masking noise?
Mm-hmm. Yeah. I guess you're asking if there's a concept of coarse-defined generation in these discrete diffusion models. I would say with masking, I don't think that there is an obvious explanation, an obvious analogy. I think it depends a lot also on the kind of sampler that you're using. So there's different samplers which might pick. I guess there's been some research looking at some samplers tend to pick more common words first and then rare words in the end, etc. But I would say there's no clean analogy. If you look at mask diffusion, if you look at uniform diffusion, I also am not aware of like very clean analogies. There is some work, I think if you go to like maybe the CDCD paper, they tried to, so this is a paper that uses continuous state diffusion, which is another really exciting set of techniques. And there might be some analogy. So you can kind of look at how it interpolates initially between two word vectors over the course of generation, and it eventually kind of chooses one towards the end. So basically, there's other techniques which might have a little bit more of that. But even I would say with those techniques, there's not a clean example to the best of my knowledge. So in brief, I think it's still an open question about whether there is any such analogy.
So it doesn't make sense to say that like the improvement in performance in the last plots that you were showing is because the diffusion language model can choose a higher level concept and then move towards that. It's not, there's no evidence for that.
I would say there's not extremely strong evidence, yeah. There's some research, but I would not say there's anything super, like resoundingly strong.
Okay, due to the interest of time, let's postpone additional questions to a coffee break and let's
Thank you.
We'll resume in about 20 minutes.
There are 8 for science slides.